Hello, my name is Sam Clinard, and I am a graduate student at the University of Utah in the Dennis Parker Lab. Over the last year, I worked for the Focused Ultrasound Foundation as a research associate, where my primary project was to develop a low-cost 3D hydrophone scanner. To conduct ultrasound research, we often need equipment to characterize the acoustic field of ultrasound transducers. This can cost a new lab tens of thousands of dollars for a commercial system. Alternatively, significant time can be invested to develop a homegrown system for lower costs. Our objective was to develop a low-cost, validated hydrophone scanner that can be easily replicated. The design uses parts sourced from online vendors and 3D printed components. All 3D files, a list of parts, and detailed assembly instructions are provided such that a graduate student could replicate this system in 40 hours and for less than $1,000. The picture on the right shows the scanning tank, which consists of 3 translation axes driven by stepper motors and lead screws. A MATLAB GUI controls an Arduino, function generator, and oscilloscope to drive the stepper motors and send and receive signals. We can do basic scans, and more complex scanning procedures could be added as needed. To validate our scanner, we compared measurements of a 350 kHz focused transducer made on our system versus the Onda hydrophone scanner. The measurements were made in the transverse plane through the focal point. Qualitatively, the images are similar in amplitude and location of the rings. We also took a vertical scan through the focal point. Again, we see the amplitude and size of the ellipse are similar. To get a more quantitative comparison, we took the horizontal cross-section through the maximum pixel in both systems' transverse images. The result is shown on the left and shows great agreement in pressure values and location of lobes. On the right, the first 2 rows are the maximum negative pressure and full width half maximum of the cross-sections. The 3rd row represents the peak negative pressure in the axial image. The data has low % difference between the 2 systems. These scans were 20 by 20 millimeters at 1/4 millimeter resolution, which takes the FUSF Foundation scanner 45 minutes and the Onda scanner 30 minutes. We also compared the radial cross-section to a simulation of the acoustic output based on the 350 kHz focused transducer's geometry. We can see the width of the main lobe and the location and magnitudes of the side lobes have excellent agreement. To determine our system's precision and repeatability, we took 5 scans of the 350 kHz transducer through the focal point, and an additional 5 scans of a 1.1 MHz plane transducer through the natural focus, resetting the scanner after each acquisition. We found the peak negative pressure and the full width half maximum of the cross-sections, as described in previous slides, for each scan. The low relative standard deviation of each measurement demonstrates the scanner can precisely measure the acoustic field. In conclusion, we have developed an open-source, low-cost, validated alternative to commercial hydrophone scanners. The system is accurate compared to a commercial system. It makes precise, repeatable measurements at a competitive speed. Further, it offers 2 significant advantages. First, it is highly customizable to fit your group's specific needs. Secondly, any improvements to software can be easily shared, which enables collaboration between groups. I'm very excited to see where this project will go. A white paper describing the project in greater detail and containing the resources to replicate the system will be published soon. Thank you for listening, and I want to specifically thank the Focused Ultrasound Foundation for introducing me to this exciting field, to Dr. Neil Cassell for bringing me on as a research associate, and all my mentors on the FUSF Foundation science team. I look forward to making more contributions to the field in the future. Thanks.